Hi everybody. So today this is an intro to how to program a neural network, and the only library I'm going to be using for this is NumPy, so let's get right to it. So I'm going to import NumPy as NP, and then I'm going to define my class. I'll call it AI, and then I'm going to initialize the constructor, so that's going to be self. I'll do inputs and outputs. I will set epochs equal to 100. So self.m equals inputs, self.n equals outputs, and self.epochs equals epochs. Okay, so let me go ahead and initialize this. So I'll do model equals AI. So it's going to take 6 inputs, 3 outputs, and I'll keep epochs constant. So now let me define x is going to equal 0, 1, 1, 0, 1, 0. So that's length 6. And then y is going to equal 0 0.25, 0 0.13, 0 0.4. Okay, so I have my variables. So what I'm going to do now is create a call function. So this will allow me to directly pass through arguments through my class object. So this will be call self x and y. And let me go ahead and make sure these are numpy arrays now, so to make it easier. So numpy.array of y. I'm going to go ahead and print x and y. So I have model over here. I'm going to do, so all I have to do is write model of x and y. So Python 3 intro to nn.py. Perfect. So we have the variables printed, so that's good. But before I get too far ahead with this, I need to create a function called sigmoid, which is the activation function, and this is what's used to like adjust the weights of the neural network model so that like it could learn from the data that's coming through. So I'll initialize this as self x and then dv for derivative initially equals false. So the sigmoid function is f equals 1.0 divided by 1.0 plus e to the power of negative x, and then it's going to be if dv is true, return f times 1 minus f. That's the derivative. Else, just return f. Okay, so we got sigmoid. So the next function I have to define is build parameters. So that just takes an argument of self. So I'll do mn equals self dot m self dot n. So I'm designing the neural network right now. Then it'll be self dot axis equals list range mn negative 1. And then I need the reverse axis for later in the video. So I'll call this r axis equals self dot axis reversed. And then I'll do for I in self dot axis self. Oh wait, let me do it this way. I can do self dot weight equals empty dictionary, self dot layer equals empty dictionary, self dot sigmoid layer equals empty dictionary, and then for I in self dot axis, it'll be self dot w of I equals numpy dot random of I comma I minus 1, setting the dimensions. Self dot L of I equals numpy dot zeros of I minus 1, and self dot sigmoid layer of I equals numpy dot zeros of I minus 1. Okay, so in order for me to have this work, I have to come here and do model dot build parameters. It takes no arguments. So we already are passing the data into the model. So I'm going to come over here now and then do for epoch in range self.epochs. This is going to be forward propagation. So I will do for I in self.axis. This will be if I equals self.axis of 0. I will do L of I equals, oh wait, I also need the bias, so B equals negative 1. So this will be x dot transpose dot self dot w of I plus b. So let me go ahead and print L of I, and then break this loop, break this loop, break this loop. Come over here. L is not, oh right, what am I doing? Self dot L. And this is supposed to be self dot L. So these are accessible outside of the class. Okay, good. So it passed through. So I'm going to now do else. So this time it's going to be, so if it's the previous one, it'll be self.l of I equals self.w of I dot self.l of I plus 1 plus b, print self.l. Oh wait, yeah, I didn't need that. Size 5 is different from 4. Um, okay, maybe it's this way. Maybe it is self.l of I plus 1 dot transpose multiplied by self dot that plus b. Let me clear the terminal. It's getting messy. Okay, perfect. So that was able to um, forward propagate that. So forward propagation is probably the easiest part of coding a neural network. So since I have that, I can do self.sigmoid layer of I equals self.sigmoid of self.l of I, and the derivative is false, so I don't need to do anything. So now comes backward propagation. Backward propagation. So now we're going to use the reverse axis that we declared over here. So this is going to be for I in self.r axis. So it'll be if I equals self.r axis of 0, first element, the error is going to equal y minus self.sl of I squared. And the delta is going to equal the error times self.sigmoid of self.l of I. dv equals true. So let me go ahead and print error and delta. Break that. Break. 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 Okay, so this is the error. This is the delta. So now what I have to do is come here and do else. So I will do print delta dot shape and self dot weight of I minus 1 dot shape, because that should equal the error. So okay, that was not yeah, this is better. 3443. Okay, so I believe the error will equal self.weights of I minus 1 multiplied by delta. So now print error dot shape 3443. Okay. So this doesn't need to be here anymore. But then delta is going to equal error times self. Oh wait. Let me do it like this. Print error dot shape and print self dot l of I dot shape. 4 and 4. Okay. Now let me cut that out. Okay, I knew there would be an error in this. So delta equals error dot transpose dot dot self dot L of I dot shape L of I. So clear that. Okay, so I'm back to the drawing board. Print error dot shape self dot W of I minus 1 dot shape and delta dot shape. Let me go back up here, break that loop, and then break that. Just a simulation of breaks. Okay, so 4, 3, 4, 3. Okay, so now let me come over here and do delta equals error times self.sigmoid of L self.L of I dv equals true. Let's see what this looks like now. Okay, 4, 3, 4. Okay. Um, so I'm gonna take away the break right now. Hopefully it doesn't error out. Okay, well, I think it worked. So I believe I have to just store the gradients now. So I'll come over here and do gradient equals empty dictionary. So over here it'll be gradient of I equals delta. And now I'm going to come over here and do for u in self.axis. This will be self.w of u minus equals gradient of u. And then I'm going to break that. Or rather, no, this is what I'm going to do. I'm going to come over here and print out the error. So I'll do print error, comma, error. So now if this all worked, let me go ahead, do reset. So let's see the results for this. So Python, or rather I probably just have it in here. Okay, so let's take a look at these errors. Let's see. This is what I'll do. I'll do the errors equals empty list, and then I will come over here and just do the errors dot append error dot to list, and then I'm gonna return these. So maybe oh, actually I could do self dot the errors. So self dot the errors, and then over here just do, so I can't return anything, but I'll just do self dot the errors equals numpy dot array self dot the errors. And before I go, I'm going to make a chart. So I'm going to come here and import matplotlib.pyplot as plt, and then I'm going to do figure equals plt.figure, fig size equals 9 by 5, and then it's going to be ax equals fig.add subplot 111, and then I will do, I'll actually come down here and do, I'll call it y1, y2, y3 equals empty list, empty list. And then I will do for x1, x2, x3 in model dot the errors. So this will be y1.append x1, y2.append x2, y3.append x3. Did I initialize? Yeah, I did initialize it. So the first one's going to be ax.plot y1 color equals red, label equals variable 1, and ax.plot, oh wait, I also have to clear the plot, so ax.cla, ax.set title, neural network results, neural network error minimizer, neural network error minimization. So then this will be y2 color equals orange, label equals variable 2, and ax.plot y3 color equals red, orange, blue, label equals variable 3, and plt.pause 0.1. Let me make sure to include the legend, so ax.legend. And then over here, I could just do plt.show. Okay, so clear that. Okay, so these variables are all behaving differently. Variable 3 is being minimized the most, while the other two variables are struggling. So variable 3 is the highest, variable 1 is the middle, and variable 2 is the lowest. Let's see. What happens if we set them all equal to each other? Because often in AI you could have two different ways to like come up with something. So let's see what 0.25 looks like. Okay, so the first two are converging. They're all converging like curves. Variable 2 and variable 3 have similar behavior. Um, you know what? I think I need to make the epochs bigger, so I will come over here and do epochs equals 250. Um, Let me make these higher, 35, 45, 25. And let me make the plot faster. So we're seeing the errors being minimized. Okay, so variable 3, which is the lowest this time, had the highest convergence rate. Um, yeah, so that's that. I think, let's see. So variable 1 is the middle highest, variable 2 is the highest. So I guess it does depend on, yeah, it depends on the inputs as well, like the concentration of what's going on. Let me turn this into a 1. I'm not gonna get rid of that chart. I'll keep that there. But let me run another one. Okay, now these three are like working in sync. Because of that one input change. So that's how they all started off, like with those values. But the blue one, which is variable 3, the lowest one this time is having the best. Okay, I will do one more. Um, I will set this 1 to a 0. So let's see how that affects it. So go ahead and run it. Okay, so now variable 2, the middle one is running. Variable 1 is also converging, but variable 3 is just going out of its way. But yeah, you know what? I think I'll just leave this at here. I think we're in a good position in this video. So there's going to be a part two intro to neural net video coming out in the next few days or maybe even tomorrow. I'm not sure yet, just trying to like figure out my schedule. But yeah, I thank you all for watching. I'm gonna keep coming out with more and more good machine learning content, so stay tuned and peace out.